In this video, we will learn Bra-Ket notation, which is also known as Dirac's notation. Learning Dirac's notation is vital to learn quantum algorithms. There are many interesting facts about Bra-Ket notations which I have not included in this video because my aim is to make this video easy so that all of the undergrad students can follow it without any problem. So let's start. In this video we will learn about these following concepts. We will learn what is the Ket notation and how can we express any column vector using Ket notation. Number 2, we will learn Bra notation and its relationship with the Ket notation. How can we convert Ket notation to Bra and Bra to Ket? Thirdly, we will learn about Ket-Ket notation and how to compute tensor product. Fourth, we will learn Bra-Bra notation. Fifth, we will learn Ket-Bra notation, that how can we express any matrix using Ket-Bra notation. And finally, we will learn about Bra-Ket notation, so that how can we compute inner product using Bra-Ket notation. So let's start. We start with Ket notation. Ket0 is defined as a two-dimensional vector whose zeroth location has 1 in it. This is the zeroth location of this vector and this is the first location of this vector. Similarly, Ket1 is defined as a two-dimensional vector whose first location has 1 in it. So in this case, I will have vector 0, 1. This is the first location. We can extend this concept to any column vector. Let's take an example of Ket 1, 0, 1. First of all, we have to see how many binary digits are here. In this case, there are 3 binary digits. So from here, we know that 2 raised to power 3 is equals to 8. So this vector will be 8-dimensional. So now we are ready to write a vector which has 8 elements in it. And because 101 when converted to decimal becomes 5, therefore its fifth location will have 1 in it. We know that we have to start counting from 0. So the 0th location will have 0, first location will have 0, second location will have 0, third will have 0, fourth will have 0, fifth will have 1. 6th will have 0, 7th will have 0. That's it. We don't have 8th location because we have started counting from the 0th location. So this was our 0th location and it has 8 elements. So this will be our 7th location and the 5th location has 1 in it. So let's do another example. In this example, I have Ket 1, 1. Once again, I have to see how many binary digits are here because we have 2 digits. So therefore, we have a 4-dimensional vector. And because 1, 1 represents 3, so the third location will have 1 in it. Once again, we have to start counting from 0. So 0 on the 0th location, 0 on the first location, 0 on the second location and 1 on the third location. This was our 0th element, this was first, second and this was our third element. Now we can express any column vector in 2-dimensional, in 4-dimensional, and in 8-dimension, in the power of 2 dimension using Ket notation. Let's see how we can do that. First of all, let's do that in 2 dimension. So we know from the linear algebra that there was a standard basis. Here we can express standard basis using Ket notation. So these are our basis vectors in 2 dimension, and this is very easy to understand. Standard basis, which is also sometimes known as computational basis. And now if I have to express this vector 7 and 3 plus 5 iota using Bra-Ket notation, then I can express it using standard basis, because I know that this is the 0th location and my 0th location has 7, so I will write 7 at 0th location. I know that this represents first location and my first location has 3 plus 5 iota, so I will write 3 plus 5 iota first location. And if I put the value of Ket0 and Ket1 here, I will get this vector. You can do that very easily. Similarly, I can express any vector in any dimension of 2's power using Bra-Ket notation. So let's write one vector in 4 dimension using Ket notation. So I have to express vector 7, 0, iota plus 3, 0 using Ket notation. I know that this is 0th location, so I will write 7. In this case, my basis will be not Ket0 and Ket1, but my basis will be Ket0, 0, Ket1, 0, Ket0, 1, and Ket1, 1. I will say 7 times 0th location, which is Ket0, 0, plus iota plus 3, iota plus 3, and because this is second location, as I started counting from 0, so I will write this 1, 0, and that's it. So I have represented my 4-dimensional vector using Ket notation. Similarly, I can represent any vector in 8 dimension, 16 dimension, and so forth using Ket notation. I think that's more than enough to learn about the Ket notation, and we can now move on to the Bra notation. Bra notation. Similar to the Ket notation, Bra0 is a 2-dimensional row vector whose 0th location has 1 in it, and Bra1 is 2-dimensional row vector whose first location has 1 in it. Very simple and straightforward. If I have Ket psi and I take conjugate transpose of Ket psi, then I will get Bra psi. I will explain what conjugate transpose means. Similarly, if I have Bra psi and I take conjugate transpose of Bra psi, I will get Ket psi. The conjugate transpose, represented by this dagger, is composed of two operations. The first operation is obviously conjugate, which is usually represented by a star, and the second operation is transpose, which is usually represented by a T sign. In conjugate operation, we change the sign of every term having iota, where in transpose we convert rows to columns and columns to rows. So let's clarify it with an example. So in this example, my ket psi is equals to 3 plus 5 iota times ket 0 plus 7 ket 1. And I have to find out what is Bra psi. And I know that if I take conjugate transpose of ket psi, I will get Bra psi. So what I have to do is that I have to compute conjugate transpose of ket psi. To that end, I will change the sign of terms having iota in them. That means this plus will convert into minus because 5 iota has iota in it. So I will get 3 minus 5 iota, and this ket 0 will become Bra 0. So I will get here Bra 0 because this is taking transpose, plus there is no iota here, so there will be no changing of sign in this term, and we get 7 and once again Bra 1. Let's represent ket psi and Bra psi in vector form so that our concepts can be clear. So ket psi is equals to, the 0th location will have this and the 1 location will have 7. So 3 plus 5 iota and 7. And Bra psi will be a row vector whose 0th location will have this and the first location will have this. So it will be equals to 3 minus 5 iota and 7. Once again, I can represent any row vectors in 2's power dimension using Bra notation. For example, if I have this vector 3, 0, iota, 7, then in Bra notation this will be equals to 3 Bra 0, 0. The reason I have used 2 binary digits here because it was a 4-dimensional vector. And the 0, 0 represents the 0th location of this vector. Iota, and because iota is on the 2nd location, so I will write 1, 0. Finally 7, which is on the 3rd location, I will write 1, 1. So far we have learned that we can express any column vector whose dimensions are in the power of 2 using Ket notation, and we have learned that we can express any row vectors whose dimension is in 2's power using Bra notation. And we have also learned that we can convert a vector in Ket notation to Bra notation and Bra notation to Ket notation by taking conjugate transpose. So now next we have to learn what is a tensor product and what is Ket-Ket notation and what is Bra-Bra notation. Let me clear the board and then we will continue. Ket-Ket notation basically gives us the tensor product of 2 column vectors, creating a column vector of higher dimension. Similarly, Bra-Bra notations also gives us tensor product of 2 row vectors. Knowing tensor product in general is very useful in quantum computing because we will be creating quantum gates using it. So let's take an example of matrix and see how can we calculate tensor product of that matrix. And then I will come back to the Ket-Ket and Bra-Bra notation. I have a matrix A which is equals to 1, 0, 0, 2, and I have a matrix B which is equals to 1, 2, 3, 0, 4, 7. And I have to calculate tensor product of A and B. This sign represents tensor product. So tensor product of A and B will be equals to this 1 times B, this 0 times B, this 0 times B, and this 2 times B. We can expand this to 1, 2, 3, 0, 4, 7. This will expand to 0, 0, 0, 0, 0, 0. Similarly, this will be 0, 0, 0, 0, 0, 0. And finally, 2 times B is equals to 2, 4, 6, 0, 8, 14. So that's the tensor product of A times B. It's a higher dimensional matrix. Now we can know about the notation Ket-Ket. I'm asked to compute tensor product of ket psi and ket phi. Then this can also be represented as simply ket psi and ket phi, because we cannot confuse this with multiplication, as these column vectors cannot be multiplied with each other. So in quantum computing, for the sake of simplicity, we just can write it as ket psi phi. These three notations, although looks different, but they all represent tensor product of two column vectors. So let's do an example. My ket psi is equals to iota ket 0 plus 7 ket 1. My ket phi is equals to ket 0, 0 plus 3 ket 1, 0 plus 7 ket 1, 1. I have to compute ket psi tensor product with ket phi. Once again, I can write it as ket. So this will be equals to iota. First I will take this term and then I will multiply, or I will compute tensor product with all of those terms. So it will become iota ket 0, 0, 0, because this 0 and these zeros get together and become a new vector of ket 0, 0, 0 plus 3 iota ket 0, 1, 0 plus 7 iota ket 0, 1, 1. Then I will take this term and I will multiply with all of those terms. I will get plus 7. First I have to write 1, so 1, then these two zeros, 0, zeros, plus 21 ket 1, 1, 0 plus 49 1, 1, 1, and that's it. This is basically my tensor product of these two vectors. I can express this in terms of a vector, and I can also express these in terms of a vector. So let's quickly express all of them in terms of vector so that our concepts are clear. So my ket psi was equals to iota 7, my ket phi was equals to 1, 0, 3, 7, and then my tensor product of these two vector was equals to a higher dimensional vector. So my zeroth location will have iota. This is my zeroth location. My second location will have 3 iota. So first location has nothing, second location has 3 iota. My third location will have 7 iota, and my fourth location will have 7. So this is my zeroth location, first, second, third, and fourth. My sixth location will have 21. So my fifth location will have 0, and my sixth location will have 21, and my seventh location will have 49. And because these are 3 digits, so I know that my vector will have 8 elements, and this vector has 8 elements. So Ket-Ket notation is tensor product of 2 column vectors. Similarly, Bra-Bra notation is tensor product of 2 row vectors. Let's do a quick example of that also. So in this example, my Bra psi is equals to 3 Bra 0 plus 7 Bra 1, and my Bra phi is equals to Bra 0 plus iota Bra 1. I have to compute tensor product of Bra psi and Bra phi, and this will be equals to that I first take 3 Bra 0 and then multiply it with both of those components. I will get 3 Bra 0 0 plus 3 iota Bra 0 1 plus, now I will take 7, this should be Bra, not Ket. I will take 7 Bra 1 and then multiply with both of those components. I will get 7 Bra 1 0 plus 7 iota Bra 1 1. Once again, I can represent all of them in terms of row vectors, which is very straightforward, so I'm leaving that on you. Now let's move to the much more interesting concept of representing matrices using Ket-Bra notation. Now let's see what Ket-Bra implies and how can we express matrices using Ket-Bra notation. Let's say we have to compute Ket alpha and Bra beta. Then in quantum computing, first of all, we don't write these terms like this because this wastes time, and this is an uncool method of writing this terminology. Instead, we write in a cool manner, which is that alpha and beta with this cross sign in between. If you look closely, then both of those are actually the same, but this saves us a few milliseconds. So if I have to compute ket alpha and bra beta, then my result will be always a matrix, and no matter the dimension of these vectors, this operation will always be valid. Let's see why it is. So I know that ket alpha represents a column vectors. So this vector will have many rows but one column. So dimension of this vectors will be m times 1. And I know that bra beta represents a row vector. So this vector will have one row but multiple columns. So the dimension of this vector will be 1 times n. And because dimension in the middle will always be equals to 1, therefore we can always multiply this column vector with this row vector. So we can always multiply them, and our result will be a matrix, and the dimension of that matrix will be m times n. Let's do an example to understand it better. So in this example, I have to compute ket 0, 0 and bra 1, 0. Now I know this is a column vector whose 0th location has 1 in it and rest of the location has zeros. I also know that the dimension of this vector will be 4 because I'm using 2 digits here. So here is my ket 0, 0. Then my bra 1, 0 will be a row vector whose second location will have 1 in it and rest of the entries will be 0. So this is my bra 1, 0. Now if I multiply these two vectors, then my result will be a matrix whose 0th row and second column will have 1 in it. Magic. So the first, this 0, 0 represents row and this 1, 0 represent a column, and then we can find where the 1 will be in my matrix. So in this case, my 1 will be at 0, 0, 1, 0 because this is 0th row and this is 3rd column. And rest of the entry of this matrix will have zeros. And what's the dimension of this matrix? The number of rows depends upon the first vector because it has 2 zeros, so it will have 4 rows and it has 4 columns. So this is my 4 by 4 matrix. Let's make this concept even more clear with a bit difficult example. So in this example, my ket alpha is equals to 3 ket 0 plus iota ket 1, and my ket beta is equals to ket 0, 0 plus 2 ket 1, 0 plus 7 ket 1, 1. And I have to compute ket alpha, bra beta. First, I should compute bra beta in order to compute this. So let's write bra beta. In bra beta, I have to take conjugate transpose of this. That means all the terms having iota, they will change their sign, and also ket become bra. So this will be equals to, because it doesn't have any iota terms, So this will simply be bra 0 0 plus 2 bra 1 0 plus 7 bra 1 1. Now I can compute this. So ket alpha and bra beta is equals to, that I write first this vector is 3 ket 0 plus iota ket 1, and I'm going to use this space also. And then I will write my bra beta, which is bra 0 0 plus 2 bra 1 0 plus 7 bra 1 1. And now I simplify them, then I will get 3, and I will get ket 0 bra 0 0. And then I will get this with this, I will get 6 ket 0 bra 1 0. Then this with this, I will get 21 ket 0 bra 1 1. Then I continue in the next line. I will use this, and this term I will get iota ket 1 bra 0 0. Then I will get 2 iota ket 1 bra 1 0, and finally I will get 7 iota ket 1 bra 1 1. Now this should be my final answer if I only have to find result in Bra-Ket notation. But to explain things clearly, I also want to express it in terms of a matrix. So let's do that. So first, let's decide what will be the dimension of my resultant matrix. To that end, let's find out how many rows my matrix will be. Because in the Ket notation, I have single digits, therefore my matrix will have 2 raised to power 1 equals to 2 rows. So I will have 2 raised to power 1 equals to 2 rows in my matrix. And in my Bra notation, I have 2 binary digits, so that means my matrix will have 2 raised to power 2 is equals to 4 columns. So now I can write a matrix which has 2 rows and 4 columns. This will be my row number 0, or the 0th row. This will be my first row, and then this will be my 0th column, this will be my first column, this will be my second column, and then finally this will be my third column. Now this term is saying that put 3 on the 0th row and 0th column, which will be this. So I put here 3. This is saying that put 6 on the 0th row and second column. So in the 0th row and second column, I put 6 here. This one is saying put 21 on 0th row and third column. So I put 21 here. This is saying put iota on first row and 0th column. I put iota here. This is saying that put 2 iota on first row and second column. So I put 2 iota here. And this is saying put 7 iota on first row and third column. So I put 7 iota here. What about this? Because I have 2 empty locations, I put zeros here. So this is my final matrix. To understand it even more clearly, let's do another example. In that example, we have a matrix and we have to express that matrix in terms of Bra-Ket notation. That will be interesting. So here I have a matrix A which has 4 rows and 2 columns. So it will have 0, 1, 2, 3 rows and 2 columns. This is 0th column, this is first column. So the entry of the matrix could be randomly 0, 1, 3, iota, 7, 0 and 0, 13. And I have to express this matrix using Ket-Bra. So first, how many digits I need to express my rows? Because I have 4 rows, so I need 2 binary digits to express my rows. That means to express rows, I will be using my bases of 0, 0, 0, 1, 1, 0, 1, 1. And then how many digits I need to express columns? Because I have 2 columns, so I need 1 digit to express my columns. This 1 is at 0th row and first column. So I express my rows using 2 digits. So I will write 0, 0. And I express my columns using 1 digit. So I will write here 1 because my entry was at the first column. Now I express this entry. So for that I write plus 3, and this 3 is on the first row. So I write 0, 1 here, and this 3 is on the 0th column. So I write 0 here. Then I have to express iota. This iota is on the first row and on the first column. So I will write here plus iota first row and first column plus. Then I have to write 7, and this 7 is on the second row. So I will write here 1, 0, and this is 0th column. So I write here 0. And then I have to write 13. So this 13 is at the 3rd row. So I will write here 13 ket 1 1 because 1 1 is equal to 3. And then at the first column, so I will write here 1. And that's it. The final thing that we have to learn in this video is Bra-Ket notation. Last, but one of the most important concepts of this video is Bra-Ket, which is used to compute inner product. Bra alpha and Ket beta. We know that this is a row vector of dimensions 1 times n, whereas Ket beta is a column vector with dimensions m times 1. In order to multiply these two vectors, m must be same as n. Otherwise, we can't multiply them. And our result of this multiplication is a matrix of 1 by 1 dimension, which we simply called a number. So our result is 1 by 1, which is a number. And this number is called the inner product of these two vectors. Let's learn it with some examples. We start with a simple example. Let's compute inner product of Ket0 with Ket0. So Bra0 and Ket0 is equals to 1 0 times 1 0, and our answer will be 1 times 1 plus 0 times 0, and that is equals to 1. If the inner product of a vector with itself is equals to 1, then it implies that its magnitude will also be equals to 1, because magnitude or norm of any vector, say ket alpha, is equals to square root of inner product of ket alpha with itself. And if norm of a vector is equals to 1, then such a vector is called unit vector. Because square root of 1 will be equals to 1, so we have shown here that ket 0 was a unit vector. Similarly, ket 1 is also a unit vector. In contrast, when inner product of two different vectors is equals to 0, then those vectors are orthogonal with each other. That means they make a 90 degree, a right angle triangle with each other. For example, ket 0 is orthogonal with ket 1 because their inner product is equals to 0. Let's verify it quickly. So ket 0 inner product with ket 1 is equals to, first I have my row vector, so I will write here 1 0, and then this one is column vector, so this will be 0 1, and my answer will be 1 times 0 plus 0 times 1, and that is equals to 0. So these are orthogonal vectors. Now let's do a more interesting example. In this example, my ket alpha is equals to iota ket 0 plus 7 ket 1, and my ket beta is equals to 3 ket 0 plus ket 1. And I have to calculate inner product of these two vectors. So my inner product will be Bra alpha and ket beta. Before I start my calculation, I must make sure that these two vectors have the same dimension, because remember, n must be same as m, and if they don't have the same dimension, then I can't compute the inner product. In this case, they have the same dimension, so I can proceed with computing their inner product. First, I write ket alpha in terms of Bra alpha by taking its conjugate transpose. So Bra alpha is equals to conjugate transpose of ket alpha, and that is equals to minus iota Bra 0 plus 7 Bra 1. Note that here I have changed the sign of terms with iota, and I have changed Ket notation to Bra notation. This is basically taking conjugate transpose. Now I can write my inner product first as minus iota bra 0 plus 7 bra 1 times 3 ket 0 plus ket 1. And now I simplify it further. I will get minus 3 iota bra 0 ket 0, then I will get minus iota bra 0 ket 1, then I will get 21 bra 1 ket 0, and finally I will get 7 bra 1 ket 1. Now recall that ket 0 was a unit vector, therefore this will be equals to 1. And ket 1 and ket 0 was orthogonal with each other, so this will be equals to 0 and this will also be equals to 0. Finally, ket 1 is a unit vector, so this will be equals to 1. Hence, this whole simplifies to minus 3 iota plus 7. And that's my final answer. This is my inner product. Now, please remember that inner product is not commutative in general. So, for real numbers, I can say that bra alpha ket beta is equals to bra beta ket alpha. Otherwise, for complex numbers, bra alpha ket beta is equals to bra beta ket alpha conjugate. So I must calculate conjugate, otherwise the right hand side and left hand side will not be equals to each other. And that's the end of this longest video that I have ever made. I have skipped many interesting concepts which were complicated and I think might not be needed at this moment. However, the concept explained in this video are essential to understand very interesting quantum algorithms we will be studying in the later videos. Stay tuned.